Okay. Thanks. First, thanks, of course, to organizers for inviting. It's really great pleasure to be back here. I guess last time I was speaking here maybe 5 years ago, something like this. Great. So I have a bad habit of going over time. So somewhere in the middle of my talk, I prepared summary of the first part, and I don't think that I will go to second one. Instead, my suggestion is to interrupt me and ask questions because it will be easier to handle things in a live discussion. So it's a story about a bunch of works done with quite a number of people. Some are in the audience. And I will tell you about one part of the story done with these wonderful people. And it's all about interplay between superconductivity, or more accurately, pairing of fermions and non-Fermi liquid in a metal. And to start the story, it's common knowledge, particularly here, because many experiments were done here, that if you take a system on the verge of instability towards some density wave order, most likely magnetic order, which can be either ferromagnetic or antiferromagnetic, and see what happens in the vicinity of this big elephant in the room, which is magnetic order, you find out that close to vicinity, there is superconductivity. And let me try to see whether it's mouse. Yes, it's mouse work. Particularly in this classical example of heavy fermion material, you see nice dome of superconductivity located right at the end point of antiferromagnetism. Less obvious story here, but you may notice that there is no line here, but there is some say there is a second ferromagnetic transition line goes right through the middle of this transition. And of course, cuprates is always under the radar or the stories, and iron-based material with stripe magnetism and superconductivity and nematic order are always here. And magnetism is not the only option. There is also superconductivity near a nematic transition, as is obvious for doped iron selenium material. And less obvious, but I will cite just one, in fact, quantum Monte Carlo study. There is also superconductivity near a charge density wave transition, happening pretty much the same way. As the system approaches a transition, superconductivity tends to develop. And this all brings me to the story that I want to discuss. How one can get superconductivity near density wave transition, or generally near particle hole instability, and why this superconductivity is interesting, why it's not ordinary BCS-ish like superconductivity. So the story I'm going to tell is formulated like this. You take a system and try to make to be as general as possible. So let's assume that we have a bunch of fermions and interacting fermions. By changing some parameter, being doping, pressure, field, you bring the system towards quantum critical point, towards some ordered state. Think about this state as either antiferromagnetism or nematic order, or ferromagnetic order, or current order, something. And the question is, what happens near this red point? Of course, experimentally, we never are at zero temperature, but as theorists, we like to play with zero temperature. So most of my story will be about what happens when you go straight along this line and hit quantum critical point at zero temperature. And there are three basic facts known pretty well about what happens when you try to approach this red dot. One is obviously that the system always finds attractive pairing channel. This is not guaranteed. There is no theorem that latest system will always find attractive pairing channel. But story goes like, tell me the opposite. I don't know about examples when the system doesn't. Oh, sorry, I know about one example when the system does not do this. But for most cases, the system always find attractive channel. And again, cuprates is always under the. They're here. So D-wave superconductivity mediated by antiferromagnetic fluctuations is one part of the story. S plus minus in case of iron-based is another. And which means that if nothing else interferes, meaning of this phrase, if you take free fermions and free fermions are interacting and you make interaction mediated by this soft boson, which softens at the critical point, you find out that yes, there is attraction. and the softer is the boson, the larger is the attraction, you get superconductivity. But there is, of course, another story. If you take the same interaction between fermions, which viewed in a particle-particle channel give you pairing, and put this interaction in a particle-Hall channel, and calculate self-energy in the normal state, you find out that the system wants to do something different. System wants to produce non-Fermi liquid physics. And non-Fermi liquid here means quite simple and detailed stuff, that if at this point in the normal state at 0 temperature, you calculate self-energy, you find out that self-energy is non-analytic, and scale says omega to some power of alpha. Alpha is smaller than 1, which means that real and imaginary part of the self-energy always are the same order and larger than the bare omega, which means that Landau criterion Fermi liquid is never satisfied. So this is what I mean by non-Fermi liquid physics. And of course, there is a window near the critical point at finite temperature where this non-Fermi liquid physics holds. And the third one, so superconductivity was one. If you neglect anything else, non-Fermi liquid is the other if you neglect superconductivity. And the third, obviously, what happens if you bring them together? They compete with each other. The tendency compete by trivial reasons in some sense. That if you take into account fermionic self-energy and think what large self-energy means, it means that you make fermions incoherent. Incoherent fermions don't have Cooper logarithm. And therefore, incoherence just on a trivial basis acts against pairing. On the other hand, if pairing wins, then pairing always gaps out low energy fermions. And by gapping out low energy fermions, it reduces, of course, scattering at low energies, which means the system recovers Fermi liquid behavior. Even if superconducting gap is 0 at some point, D-wave superconductivity still give you perfect Fermi liquid at low energies. And it should work. Interesting. Let's see. It works this way. Okay. And in this story, pairing and superconductivity come from the same source. And it's because the same interaction. You just look interaction face like this, it gives you superconductivity. You turn around and look into different channel, it gives you non-Fermi liquid. So it's the same interaction, which means the two phenomena have same characteristic scales. And this is interesting problem for theorists because naturally there is no small or large parameter that will tell you one effect is much larger than the other. So this one is still not working. So let me try to use old-fashioned way. So the goal of my talk is just to analyze this competition between these two phenomena. And one just acknowledged slide. Not every problem near a quantum critical point is under what I'm going to talk about. I will consider a subset of systems in which by one reason or another, and it's really one reason or the other, bosons are slow mode compared to fermions. And of course, example of phonons comes into consideration. This is what makes a Leashberg theory. Phonons are slow compared to electrons. If we think about superconductivity mediated by collective modes of electrons, it's not that obvious, but Landau damping plays a role. And so if we consider Landau overdamped soft bosonic excitations, then without going into fine theoretical print, bosons are slow mode compared to electrons. And if it's like this, there is a very simple thing. Why it's good for theories? Because there is a set of rules. And York in his talk will also be talking about the same set of rules. And the rules is quite strict. Namely, we know in the situation how to solve the problem. And we know that there is potentially small parameters that allows us to do what we are doing. And what we are doing is this. We have two ingredients that tells you two pieces of information about the system. One is self-energy, which account for non-Fermi liquid physics. And another is what is called anomalous pairing vortex, which you put in the system to probe pairing between fermions. Both are generally a function of momentum and frequency. This is, of course, omega minus omega k and minus k for the vortex, or k and omega just simply for self-energy. And the rule is that we know how to get rid of k dependence. For self-energy, it's pretty straightforward. You just calculate k-dependent, omega-dependent self-energy and find that omega-dependent is parametrically larger. For pairing vortex, what you do, you tune or you project into the most attractive channel. And by doing this, you essentially eliminate k-dependence by taking it as in the most attractive pairing channel. And long story short, what it tells you at the end of the day, that k-dependence is taken, and you have problem of two variables, both depend only on frequencies. This already reduced phi projected in a particular spatial channel. And these two guys compete with each other. So the story about competition between non-Fermi liquid and pairing is a story about competition of two frequency dependence variables, which in theoretical words means that the problem becomes effectively one-dimensional. It's 0 plus 1 dimension if you like. And even simpler, we know how to write down equations. These equations, you will see another version of this equation in SYK model, which is similar but not identical. There is equation for pairing vertex. There is equation for self-energy. Both depends on frequency. And competition here is again on a trivial level. Sigma is in denominator equation for phi. Phi is in denominator equation for sigma. So the larger is phi, the smaller is sigma. The larger is sigma, the smaller is phi. It's simple as this. The quantity which really important for me is what is labeled here chi L as a function of transverse frequency in both equations. This is our interaction. I call it chi because it's like bosonic susceptibility. So it's interaction mediated by some effective boson. But you saw this equation before. I'm sure there's a number of people working on the Ashberg theory. And so if you look at any normal situation, people worked on this equation for a while, then this is normally called the Ashberg theory. And this chi, for any situation when you have a Fermi liquid and your boson is gapped, then at small frequencies, this chi reduces to a constant. If chi is a constant, then you get Fermi liquid theory. Namely, you get BCS-ish like pairing, you get self-energy, which is linear in omega, so you preserve Fermi liquid, higher powers give you damping. If you look at solve for phi, to force approximations, this is a constant. Then I have a lot of details of why the Ashberg theory is different from BCS. It's a story about high frequencies, but qualitatively, it's all the same physics. You get pairing in a Fermi liquid. What's special about pairing at the quantum critical point is that chi is qualitatively different. Because you have a pairing mediated by a massless boson, then propagator of this massless boson, local propagated, integrated along the Fermi surface. This is a story about exact integration over momentum with fast electron and slow bosons. This chi actually diverges at zero frequency. It diverges at some particular power. That's why it's called gamma model. The power is labeled by gamma. I will give you examples on the next slide, but I want to emphasize here there is one qualitative difference. In any Fermi liquid, chi is a constant and only decays at low frequencies. Then you can say to first approximations like BCS. But if you have your interaction that diverges at zero frequency, then you cannot do BCS. And in fact, if time permits, and I will come to the second part of the talk, you will see that pairing is really qualitatively different from BCS. Okay, this is a busy slide with a lot of names in it, but I'll just want to give you two examples, both are in 2 dimensions. If you consider pairing by nematic fluctuations, this is the form of your bosonic propagator, this Landau overdamped omega over Q, and then all you have to do is to integrate chi along the Fermi surface because integration transverse to the Fermi surface is already done in fermionic propagator. So when you do this, you get exponent 1/3. If you look at pairing by antiferromagnetic fluctuations, again, details aside, you get linear in omega term because Q is finite. You do the same integration, you get gamma 1/2. And then there is a bunch of different gammas, including the ones that Jörg will be talking about in SYK model of dispersionless fermions coupled to Einstein phonons. So what I will do, I will take gamma. Let me go back for a second. I will just take gamma as a parameter. Of course, we don't have gamma as the free parameters that will vary. We have particular models, and each has its own gamma, except that people created models with varying exponents. But what I want to do is to create phase diagram, which will have gamma on one side, temperature on the other side, and then you pick the value of gamma and ask what happens. So I will try to find out what happens with generic phase diagram. And the first thing to do, and in some sense it could be the final answer in 5 minutes, you can ask computer to do a simple thing, to ask who wins. You have two tendencies that are built in the two equations. The system can either remain normal, down to 0 temperature and become non-Fermi liquid, or the system can develop pairing instability and become a superconductor at low temperatures. And again, there is no small or large parameters that could distinguish between them unless you introduce artificial n and do expansion with n, which is a good thing to do theoretically to distinguish between two phenomena. But generally, two phenomena are of the same order. And so computer should just put the equation in a computer, and computer should tell us who wins. And computer simply tells you pairing wins. Superconductivity is a winner. Great. Meaning, you solve linearized gap equation, you ask for the onset of the pairing, and you find a finite temperature for the onset of the pairing. You go below this temperature, phi becomes non-zero, sigma becomes Fermi liquid-like, so situation is like I described when superconductivity is emerging. You get some fancy behavior at low, small gamma. Don't pay much attention to this. This is because by constructions it goes into what's called unconstrained BCS when you get interaction which is constant, but you don't put upper limit. Why we're doing this? Because it's for any gamma, any non-zero gamma. You don't need any upper limit in the theory. The fact that interaction diverges at low frequencies and decays at high frequencies. And this means that all equations are non-divergent in the infrared. These are equations are non-divergent in the ultraviolet. So you don't need any upper cutoff in the theory, any lower cutoff, anything. So you just get it. And it was done in various occasions in models interacting by collective bosons and SYK models, whatever. It's always give you finite temperature, which means I'll put the same on difference on next slide. Yes, this is what I said. In some sense, I can say, okay, this is the end of my talk. Superconductivity wins, great. This is what you get. You get a normal state. If I put, as I promised, phase diagram, temperature on vertical axis, gamma on horizontal axis, there's a line here. I put a TP because it's still onset temperature for the pairing. To get superconductivity, you know, you need to look at superfluid stiffness and see when superfluid stiffness becomes of order of temperature. But nevertheless, on a mild field level, when you ask what is the onset of pairing, it's here. And this is where my talk starts, in fact. Because I will tell you that phase diagram is a little bit more complex than just one line. And in the first part, what I will try to do, and I think this is what I will eat all my time with this, I will try to argue that there are two different superconducting phases. And there is a topological transition between the two. So there is topology involved in this system. In fact, there is a lot of topology involved here. And I will try to argue that this particular gamma equal to 2, which in fact, if you go back and ask what is gamma equal to 2, this is the case that was most studied in decades. It's a case of electron-phonon interaction in a properly defined limit when the Debye frequency goes to 0, but coupling constant between electrons and phonons remains finite. People starting from late 60s studied, of last century, by the way, studied this in some details. Okay, so here is what I will try to argue, that there are two different phases, and there is a 0 temperature phase transition between the two. And then, as you can imagine, of course, if you have a transition point, you expect that there are some lines coming of this transition. So the whole phase diagram will be more complex than just even this. Okay, let me give you the reasoning why particular exponent gamma equal to 2 is special, and why the system behavior when we try to change the exponents towards gamma equal to 2 becomes somewhat interesting. In fact, if you if we see what I will tell you in the next few minutes, you may say that there is not one phase topological transition. There is infinite number of topological phase transitions, but you will see. So let me give you the argument. The argument, in fact, is very simple. And it goes like this. Let's just compare interactions on two axes. One is the one that theorists like, Matsubara axis. Theorists like, because it's easier to do calculations on Matsubara axis, and also because pairing interaction is real on Matsubara axis. Then the stuff that I mentioned at slide number 2, in fact, of the talk, is that the system always finds an attractive channel. I assume this. I already projected my interaction in an attractive channel, which means that on Matsubara axis, interaction is attractive and it's real. So when I put like this, I put positive sign for interaction means attraction. That's just convention of sign. I take this interaction, I convert on a real axis. I can solve for the pairing on both Matsubara axis, which is great for thermodynamics. But if we want to study density of states, when we want to study transport, we of course need to know what happens on a real axis. So it's trivial to convert this interaction from Matsubara to real axis. You get this formula. And on the real axis, interaction is complex. Not surprisingly, we know that any solution for the gap on the real axis involves real and imaginary parts. The imaginary parts is what give you non-trivial transport, etc., not trivial RPS results. And then let's look at simple sign of interaction. So as I said, on Matsubara axis is attractive for any value of gamma, nothing special at gamma equal to 2. But if you look at real axis, you find something funny. Of course, you may say, well, I don't care about sign of complex interaction. What should I tell about the sign of real part if there is imaginary? But still, let's do it. You look at the sign of real part of the interaction, and you find that it's cosine pi gamma over 2, which by trivial math means that it's attractive, great, but only for gamma smaller than 1. If you go to gamma larger than 1, it's technically repulsive. And the most repulsive at gamma equal to 2. And then you say, aha, this is complex interaction, so why should I worry? But let's look at the sign of imaginary part of the interaction. And it's sine pi gamma over 2. So you see that this guy vanishes at gamma equal to 2. And then you have a very interesting and unusual situation when on one hand, if you look at Matsubara axis, your interaction is purely attractive. You look at the real axis, your interaction is purely repulsive. And then you ask the question, what the hell is going on? You can solve for the pairing on the real axis, you can solve for the pairing on Matsubara axis. And supposedly you should have totally different results on the two. So this is what makes me think that there is something special about the exponent gamma equal to 2. And by proximity, there is interesting physics going on when I go between, say, exponent 1 and 2, and even exponent smaller than 1. Great. So let's see what happens. Let's again ask computer to solve the problem. And on Matsubara axis, as we expect, nothing special happens, at least with this solution. When we change exponent, I just give you some examples for some exponents, if you can see them here. It's always the same gap, and it's normal in the sense, because this is what for anyone who was involved in solving, say, Liarsburg equations, and even generally, what you expect for superconducting gap. You expect it to be finite at small frequencies. This is what we call superconducting gap. And we generally expect it to go away at large frequencies, because we understand that if you go to energies, very, very high energies, you don't expect any trends of superconductivity left there. So the gap is a constant at small frequencies. It goes down at large frequencies as expected. You do it for any value of gamma, technically below 3, and you get the same results. Okay, let's convert. We can convert solution by using high quality. High quality is 10 to minus 5, in fact, Pade approximant. And this gives you very high quality results on the real axis when you convert from Matsubara to real axis. And we also converted equations and solved equations on the real axis, and we got the same results. So there's two approaches which give the same result. And here's the story, that if you take gamma between 0 and 1, and even didn't bother showing you all these results, attraction on both Matsubara axis and real axis, not much difference between solutions on both axes. But if you go to larger gamma, when you start seeing the stories that interaction becomes it's repulsive on a real axis. You start seeing how gap function reacts. Gap function starts oscillating on the real axis. Both real part of the gap and imaginary part of the gap, both are oscillating out of phase. And you can say, well, by itself, oscillation is not a big deal. You can see what happens, for example, here. One oscillates, this is imaginary part oscillates, real part is almost just regular function. It's not a big deal. But there is one big deal here. Namely, that if you look at the phase of the gap, phase is delta is equal to mod delta e to I eta, and eta knows about the ratio of imaginary to real part of the gap, and you plot the phase of this gap function as a function of frequency. And here you find something interesting. The phase start widening by 2 pi's. So it's the same plot, replotted in terms of the phase. And as a function of frequency, you see phase start jumping by 2 pi's. So you start having finite number of 2 pi's phase accumulation. The word topology immediately comes into consideration. And this is what I meant, that at high frequencies, oscillations are not big deal, because when one component oscillates, another does not, then the phase is slowly oscillating around a constant value. It never jumps by 2 pi. There are 2 pi phases here, and you can plot them as a function of gamma and call it in any way, but some picky theories can say that there is a bunch of topological transition where you see here, because you start changing gamma, and at some particular values, this is just plot chosen close to gamma equal to 2, you see the phase jumps by 2 pi. So the number of 2 pi phase slips jump by 1. Great. Now we have an interesting situation. On real axis, the phase of the gap jumps by 2 pi, obviously reflecting the fact that some systems, in some cases, the system wants to react to interaction being almost repulsive. On Matsubara axis, there is completely regular behavior, which is, of course, a reflection of the fact that interaction is completely attractive on Matsubara axis. But if you have phase slips on real axis and nothing on Matsubara axis, when you rotate, something should happen. Phase slip should go away at some point, which means it should be vortices. Dynamical vortices in the upper half plane of frequency. And this is what I'm going to study next. And here is the result of the analysis. Since we can, again, we can do PADE, we can convert equations on complex plane and solve in a complex plane. It sounds fishy, but in fact, it's not that fishy. Okay, so here is what comes out. The plots here are plots of the phase of the gap in the complex plane. Vertical axis is imaginary part of frequency. Real axis is real part of frequency. So if you like, this is real axis. This Matsubara axis. This is complex plane. And we're talking about dynamical vortices. And we see what happens. As gamma increases, you start with smaller gamma. And the color here is color of the phase. And the red dots, which you see here, are the vortices. Vortices are the point where modulus of the gap goes to 0, and the phase is undetermined. And if you take a circle around the point with no matter how small radius, your phase wind up by 2 pi. You do counterwise variation around the point, counterwise circle around the point. And you see that as gamma goes up, the fourth vortex appears, 2 vortices, 3 vortices, 4 vortices, etc., etc. This is what I showed before as this number of phase slips going up. Where the vortices come from? They come from lower half plane of frequency, where the gap function doesn't have to be analytic or anything. And by the way, vortex is 0 of the gap, not infinity. So vortices are perfectly allowed in the upper half plane. They don't violate analyticity of the function. Anti-vortices cannot come in the upper half plane, because anti-vortex would mean that the gap amplitude goes to infinity. And you see that the number of these vortices goes up, 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 as interaction on the real axis becomes more and more repulsive. And the difference between real and Matsubara axis becomes more and more pronounced. And finally, we come to the interesting point, gamma equal to 2. when the number of the vortices becomes infinite, and blue, this is two plots here. One plot is the phase of the gap, and again, red dots are position of the vortices. You see that they continue at all frequencies. And the second plot is log of delta, which means that when delta goes to 0, log of delta goes to minus infinity, and you see minus infinity dark blue here, and you see clearly position of the points when there is a dark blue. This is a one-dimensional array in vortices. And at this stage, let me just speculate for a second. It's really, well, we know how conventional superconductivity gets destroyed by abrikosa vortices. And you know that vortices produce a lattice. Here we're dealing with one-dimensional systems, and we talk about dynamics. But we see a one-dimensional array of vortices. So vortices come in, their number grows, and they form as array. I can even analytically know the formula for this line. So this line really goes up to infinity, which means that we have infinite number of vortices in the system. And let me go off script for 10 seconds. There's an interesting feature here. We know from textbooks that Matsubara, why we can use Matsubara axis and then obtain the function on everywhere, including real axis. Well, because the statement was that if you want to continue from Matsubara axis, there is a unique way to do this. And when continue from the discrete set of points on Matsubara axis, don't worry that there is a discrete set of points. There is unique continuation onto the whole analytic continuation into the whole upper half plane. So you get uniquely the gap function. Great. If you take the same argument, then the argument does not apply necessarily to vertical Matsubara axis. It can apply to any infinite set of points on a complex plane which accumulate to infinity. I take these points, 1, 2, 3, 4, 5, 6. This is a set of points whose number is infinite. They accumulate at infinity. And you know what happens with the gap in all these points? It's 0. So if I technically continue from this using textbook examples, I will get 0. So the question, how in this situation I get a non-zero gap on the real axis, how I get non-zero gap on Matsubara axis? And the answer is something that is always put as a fine script in the textbooks. The fine script, if there is no essential singularity at infinity. Here is, I guess, the only example I know where there is infinite set of zeros, which goes to essential, and then if you go to infinity, there is essential singularity there. So because of essential singularity, the standard theorem doesn't work. But it also tells us that something really unusual happens. That the whole stuff that why you get a solution for the gap everywhere in a complex plane is due to the fact that at infinity, there's essential singularity. Yeah, okay, I'm coming to until the end of the first half. Okay, density of states. I think York will show the picture also. Let's see what happens with this particular point, or when we approach this point. Let me remind you very quickly, the density of states in the conventional superconductor is something that you know from textbooks. There is a gap. It really should be gap if everything is plotted at 0 temperature. And then singularity, H singularity, square rootish behavior near H singularity, and then density of states is the continuum and goes to a constant at large frequencies. This is what we get for arbitrary gamma smaller than 2. Qualitatively the same as BCS, right? There is a gap at small frequencies. Then there is the H singularity. And there is a continuum, but you start seeing some oscillations in the continuum. And this oscillation is nothing but the oscillations of real and imaginary part of the gap that I showed you before. But now let's come to gamma equal to 2. And when we come to gamma equal to 2, you find something completely different. You find out that there is a bunch of delta functions here. Instead of, there's no continuum. It's a really qualitatively different behavior for this particular gamma from anything that we know before. Let me quickly put here, so I put everything here. Roland Cambesco, who first noticed this back in 1995, I guess, put a nice explanation, which I think is reasonable. He basically said that, yeah, if you want to, let's skip details, but basically he said, yeah, let's take gamma equal to, I already mentioned, is the case of electron-phonon interaction when effective Debye frequency, dressed Debye frequency, not the bare one, goes to 0. And so let's calculate self-energy in this situation. The self-energy has a singular piece which contains Debye frequency in the denominator, but nice feature is that this piece cancels out in the gap equation. And incidentally, I'm saying too many words, but still, there's a lot of stories about inapplicability of Migdal-Ashberg theory and coupling is of order of 1, which is all true about normal state. But beauty about Ashberg theory for superconductivity is all this formally divergent piece cancel out in the gap equation. So we have a perfect non-divergent theory for superconductivity. So anyway, this part of self-energy cancels out, but what is left over is if you convert it from frequency to time, you find that it's linear function of time. So it's just like retardation or potential due to interaction grows up with retardation. And it's just function in a linear potential. Only everything again, instead of space, there is time. So potential grows with retardation. And of course, function, so particle wants to self-trap in this growing potential. And this was his explanation for this bunch of delta functions, which I think is a good explanation. Okay, so I'm coming to the end of the talk. I just want to emphasize one thing here. Topological transition at gamma equal to 2. Why I think that there are two different phases? Well, it comes actually from this. I showed you these points, blue points. This is where delta goes to 0. But you see this other set of points which are approaching, which are on the real, almost on the real axis. These are points where the gap goes up. These are anti-vortices. So you start seeing something interesting. Anti-vortices come to approach real axis. And just 2 slides and I will be done. So let me just show how it works. You don't need to do Pade only in the upper half plane. You can solve in fact, you can solve for the gap everywhere in the complex plane. And you find that for gamma smaller than 2, the gap is analytic. Great, and everywhere in the upper half plane, there are vortices there. But in the lower half plane, there is a line of anti-vortices. Anti-vortices means that delta goes to infinity. And as you approach gamma equal to 2, this line approaches real axis. You can see it from here. And what happens next? Well, if you look formally what happens next, this line wants to go into upper half plane. And you can say it's nonsense. It would mean that the gap function becomes non-analytic in the upper half plane. But doing this, it clears up lower half plane, and the gap is fully analytic in the lower half plane. Then how to get the results back to normal, how to get analytic function in the upper half plane, interchange the two, which means interchange retarded and advanced functions. And if you want another wording, go into different Riemann surface. So basically what happens here in one phrase, for gamma larger than 2, you still get solution, which is analytic in the upper half plane, but you need to go to the different Riemann surface. And this, of course, means that there is a topological transition. When you go to different Riemann surface, you find situation goes back. The vortices start moving away from the real axis. And it looks like situation really is just like almost symmetric with respect to modulus of gamma minus 2. So the system becomes more and more normal. But you look at the, let me put everything here right. Look at the density of states. And this is really the last slide I want to show. And you can ask, well, the density of states for gamma smaller than 2, gamma larger than 2, let me put it here. Gamma smaller than 2, gamma larger than 2, seems very similar. Gap and continuum in both cases. There is a transition in between when this crazy delta functional behavior appears. And you can ask, what's the difference between these two cases? There is a difference. The difference is that if you look what happens with this H singularity, you find formally non-integrable singularity. This, if you integrate this guy for gamma larger than 1, you get infinity, which in physical terms means this. If you take a system with finite number of states, you don't integrate in infinite limits. You start seeing something like Bose-Einstein condensation in frequency domain. Namely, start seeing how level appears, H state appears, whose degeneracy is proportional to the total number of states in the system. So you start seeing how conventional wisdom that your excitations are gapped and then there's a continuum breaks down if you go to new superconducting phase with large exponent. And instead of saying many words here, basically what happens that you take all these delta functions, and when gamma larger than 2, spectral weight from all the delta functions goes into just one peak, which acquires spectral weight from all delta functions. And this is how it becomes a macroscopically degenerate state, which completely changes the game. And the larger is gamma, the more states go into this level. And I already showed this, and I said that I have only time for conclusions of part 1. So this is what I'm doing. So conclusions are this. Generally, there is a competition between non-Fermi liquid and pairing. Pairing wins, but the gap function on the real axis is very different from what you expect in BCS theory. And there is a reason for this. And pairing interaction is attractive on Matsubara axis, but repulsive on the real axis if gamma is exponent larger than 1. And dynamical vortices reflect this. They just like abricosal vortices penetrate into the system as you increase the field. Here, increasing gamma means the same as increasing field in some sense. Vortices, only dynamical vortices, penetrate into the system. Their number increases. They form one-dimensional array and create density of states, which is a set of delta functions. There are 2 states for gamma smaller and larger than 2. What I did not say, and what you understand that what would be in part 2 and part 3, is that just like abricosal vortices destroy superconductivity, I argue that this dynamical vortices also destroy superconductivity, which brings me, after all the stuff that I'm supposed to talk about, but obviously have no time, to the phase diagram, which, in addition to the 0 temperature transition between 2 phases, and the slide that we started with, also contains 2 lines coming out of this critical point, which is expected. If you have a critical point, you expect the transition line coming out of this. And so argument is that there is a really pseudogap behavior, which in this example stretches down to 0 temperature. And this was the real intention of all this, to find out whether you can get pseudogap that goes down to 0 temperature as a real phenomenon, not partly blah, blah, blah phenomenon. Okay, I'll stop here. Let me just, put the names and faces of people with whom various aspects of the problem have been done. Some are sitting here. And again, thank you.